I'm going to start, I'm going to finish with this slide that is actually about integrating biology. And this is the context of everything we do at this moment. The second slide is perhaps the most normal start, where what I say is what are we going to talk about. We are going to talk about where are we now as a field, where are we heading to as a field, which is three-dimensional electron microscopy, mostly from the point of view of the analysis of individual macromolecules, single particle analysis, and how the different topics are going to be scheduled in the different lectures of the course. My name is Carazo, and you see Instruct Image Processing Center. Well, Instruct is actually the major source of financing of the group, and it's about creating the infrastructure for the next years, for the next decade. And our role there is in structural biology. Instruct is made of a large collection of member states with 16 Instruct centers, and basically it provides access to these centers to anybody in these countries. So really it's a good way to get access to very advanced infrastructures. These are complicated slides, but just to say 16 centers that give access to 128 technological platforms that we are starting. We have received at the very beginning 23 proposals already for multi-site access, and everything is running and everything is going well. Okay, so with that is the context of our group. Let me introduce you a little bit what I'm going to talk in the first lecture. I'm going to talk of some of the basics of 3DM, and I will make connection of the other people that will take these basics into the details. And at the beginning you are going to have some lectures, and at the end of the day you are going to have with your computers, we have a cluster, everything that is implemented in software, and everything has been set up nicely in the cluster so that you can access, and you will make a lot of hands-on with images there. So I will just talk about the basics and who is going to introduce them in more concrete terms. And then I will present sort of a vision of where we are on 3D electron microscopy from the technical point of view and from the knowledge-based view. And of course everything related to how it's going to be taught in the course. The basic is as simple as that, this is electron microscope. Okay? I assume that most of you already know what is an electron microscope. This is a basic thing in which you have, that's a source of something, that is electrons in this case. In the next course, the source will be photons produced by a synchrotron. You have some ways to channel these things, electrons, to the specimen, normally through condenser lenses, and then there is an interaction of these electrons or photons with the specimen, and the interaction of this electron with this object creates the image over here. And this interaction is actually dictating how these images are going to be formed. And how these images are going to be formed dictates how are you going to treat them. It's very obvious. Depending on which is the interaction of the radiation with the specimen, there is some information that is learned about the specimen, and we have to derive that information from the images. Just very basic things. You are used to optical microscopy, and the wavelength of light, visible light, is in Angstrom something like 5,000 Angstrom. And if you remember your very basic physics courses, these 5,000 Angstrom have to be a limit of resolution, about. Okay? So how can we go beyond 5,000 Angstrom resolution? Well, by going to other types of optics, or to use another type of radiation with a shorter wavelength. Okay, these are the electrons. And the electron have actually a wavelength of about 0.02 Armstrong at a typical accelerating voltage of 300 volts. So you have really a very short wavelength, 0.02 Armstrong. Typically, one atom is 1 Armstrong. So you have the resolution to see an atom in 50 slices. Okay? You are never going to reach that for many reasons, but the most common one is that we have huge aberrations in electron microscopy that in optical microscopy we do not have. I mean, we have been able to correct for many of them, and we are totally hitting the limits of wavelength, and for that we have to think in other ways to form images. But in electron microscopy, really, we are so far away from hitting the limit of wavelength that just thinking in typical wavelength limitation and things like that is more than enough. More than enough, just to give you an idea of which are the size of the specimen we are going to be dealing with electron microscopy. We want, I mean, electron microscopy has appeared because we wanted to get higher resolution than optical microscopy. If you are going to see something at a lot of detail, it's because probably it's not going to be very large. So typical scale for single particle analysis is in the order of 200, 300, 400 Armstrong big specimen to 20, 30 Armstrong big specimen. So this is the typical range in which we are going to move. Typically a few hundred Armstrong big specimens. The largest specimen, thing like the ribosome, things like that. So this is for the field of single particle analysis, that is the analysis of macromolecules, isolated micromolecules by electron microscopy. This is what is going to be the main focus of this course, the analysis of macromolecules, single particle analysis. There are other ways to work in electron microscopy, of course, and one that you probably know, or you have heard of, is electron tomography. In electron tomography, we are going to see small cells or whole organelles of the cell at normally a resolution 1/1 of resolution worse than for single particle analysis. So electron tomography is the way to get the cellular context for thin images, for thin cells. If you have a macromolecule and you are making the question, the macromolecule in the tube, does it resemble the macromolecule as it is in the cell? Then electron tomography, by providing you access to at least sections of cells, gives you the capability to see the 3D structure in the context of the cell. This is for small cells, up to, say, half a micron, something like that. Why? Because electrons are absorbed by matter. So if you put more matter, then the electrons just do not go through. Or if they go through, you don't know what to do with them. Okay? So we need other sources of radiation, and this is the X-ray microscopy course that will be after that one, in which by using photons with the synchrotron, we are able to go to 10 microns, that is closer to an average cell. So we are going to concentrate in single particle analysis for this course of electron microscopy. I just mentioned that there is another area of research of electron microscopy that is called electron crystallography. That is very simple. You know all the X-ray diffraction work in which they need 3D crystals. Okay, this is complicated. What about if some type of macromolecule are more comfortable in a two-dimensional environment? They may make 2D crystals, typically the membrane proteins. So if we had membrane proteins, if we had 2D crystals, well, we had something that we call electron crystallography to make the connection between crystallography, where they need 3D crystal, and electron crystallography, in which we need 2D crystal. And we need 2D, and we cannot have 3D, because the same thing that matter absorbs electrons, and if you put too much matter, you don't have electrons at the end of the specimen. So basically, this is the context of the resolution and the sizes we are going to have. It is crucial to understand the relationship between the specimen and the image. It's very clear because you have the radiation, whatever, the radiation is going to go through the specimen, and the image is going to be just an account of the interaction of the energy with the specimen. Depending on that interaction, you will have a certain type of information or not in the image. Okay? So, you may see that there is a formula here that is in gray, meaning that I'm not going to talk about that, about the formula, but just to introduce, because somebody else will go into that, but just to introduce a few concepts. In physics, I am a physicist, and the number of people that are going to be talking to you during this day are physicists as well. We love first principle. So we have interaction of something with matter. So the first thing is it almost doesn't interact. So let's try to understand things in the limit of almost not interacting. So this is the weak phase object approximation. If my specimen is almost transparent to the electrons, then I have a very simple way to understand the images in terms of the 3D structure. If the specimen is not so transparent, then my images are much more complex to understand in terms of the 3D structure of the specimen. Some of you are coming from material science. Do you think that your high atomic number materials are going to be very transparent to the electrons? No. So all these approximations break. So you cannot work in the limit of phase, weak phase object, and everything I'm going to say is not possible. You have to go to another mathematics. Okay? Because in the limit of the electrons almost don't see the specimen, in that limit, the relationship between the image and the 3D volume is very simple. It's exactly the same that you are used in your everyday life to see. You are used to see radiographies. You are used to have a broken arm and go to the doctor, and that doctor is going to try to arrange for you a radiography. And the radiography is just a projection of the 3D structure into a 2D plane. And this is exactly the relationship that exists between the 2D images in the electron microscope and the 3D object. A projection in very quantitative terms, okay? A projection means that when you have an image and you measure a certain density here, the amount of density you measure is actually the addition of all the densities that the electron encounters as it goes through the specimen. Okay? So it's a quantitative projection. It's called X-ray transform. This is a line integral and things like that, but it's simple. The density you see in the specimen is really the addition of all the densities the electron is seeing as it goes through the specimen. This is the relationship between image and 3D volume. Exactly the same that you see in medical imaging. The mathematics, the physics is completely different, okay? Of how CT works and how X-ray interact with matter and things like that. But at the end of the day, the beauty is that you get that. And of course, that means that the two fields, medical imaging and X-ray microscopy, they can work together, trying to solve these equations and go to the 3D structure. And we have done it. I mean, we have for more than 8 years, we have an NIH project with the biomedical people, because it's exactly the same issue. Okay, fine so far?
Just a question. On that first slide, there was the inelastic scattering is negligible compared to the elastic.
Yes.
Does that mean that it is transparent?
Yes.
Especially on this one.
is basically transparent. It's the weak phase of the thing. Yes. So, well, if everything sounds complicated, okay, I hope it's not so much, but it may be. All of you have some approach already to this technology. But understand the interaction of the specimen. I'm talking of the specimen and the X-ray. The X-rays are going to go through and are going to interact with everything, with the table, with all the metals around and all that. But I am talking just the interaction of the specimen with the electron. As your electrons are more and more accelerated, as typically 300 volts, they go faster, they see less. So this approximation of your specimen is almost transparent to the electron is more and more correct as you go to higher voltages. So the case of the 1 billion volt in which you had to make the alarm sound was because of the interaction of the electron with the microscope itself, not with the specimen. Okay? So, but everything I'm telling you is too simplified, because you want to go to high resolution, I suppose. And if you want to go to high resolution, you need to take into account things that are not so nice. And any optical system, because we are not perfect as humans, has the following property. One point that axiomatically is something infinitesimally small, when it is imaged by any optical device, it has a finite extent. And a small point becomes a big point because your optical system is not perfect. And the point is converted in something that is called point spread function. Okay. The point spread function is normally worked in the electron microscopy field in Fourier space. This is absolutely crucial to go to high resolution. And because of that, it will be treated today as a separate talk by Javier. Okay? So I'm just introducing that we have to understand what we are doing. First principle, our images are like radiographies of my broken arm, are projections of my 3D structure. One point is a point. Okay, this is first order. Second order, forget it. An infinitesimally small point becomes a big point. And this big point is the one that you have in your images, is the one that it is in the reconstruction, is the one that limits your resolution. So you have to understand very well what do you have, because you will have to correct for that. Technically, you have to be convolved, correct for the CTF, whatever you want to call it, but you have to make whatever you can to make this point spread function smaller. Okay? So this will be covered by Javi this afternoon. But at the end of the day, why we are not happy with the projection images? Why medical doctors are not happy for many things just with the radiography? Well, because you may see this projection image and you think you have a hand, and what you have is a radio dancer. Okay? So you have made a very serious misjudgment of what was the 3D structure by looking at just one projection image. So you have to come from this projection image, you have to be able to recover the 3D. Okay? Intrinsically, from 1 2D, you cannot recover 3D. Because this is like you are gaining one full dimension for free. And this doesn't exist in life. So the single way to get from one to get this 3D structure is by combining many 2D images. And this is very obvious. You don't know how big is my nose. If I am just talking to you like that, I have to be sideways, and then you start seeing how big my nose is. But you can go through the mathematics of that, mathematics from the beginning of the 20th century, so it's about 1 century old, nothing new, but they explain that we need to get this 3D structure by combining many 2D images. And this has been done. This is done every day in the clinic. When you go and you take a CT, what does it happen? You are told to lay in a bed like that, and then the machine is something like this rounded thing. What is this machine doing? It's taking many radiographies around you. You are a very precious specimen, so you are not going to be tilted, moved, or anything like that. You are sitting here, and the whole machine is moving around you, taking many projection images. And the combination of these projection images is actually the way to get the 3D structure. Is that the point? So we have to make the connection of electron microscopy images, projections. Even if the physics is different, the mathematics lead to the same equation in medical imaging than in X-ray, than in electron microscopy imaging. We have projections. We do have ways to get around that because every day this is done thousands of times in any country. So we do exactly the same like that, and we do a tomographic reconstruction or 3D electron microscopy basics. That is to say, listen, from any projection image I cannot derive the 3D structure, but from a set of 2D projection images I can derive the 3D structure. This is intuitive. Intuitive, it cannot be, it's a book like that, okay, of theories. So I don't pretend that to be intuitive, but we will actually devote a complete talk of how do you do a 3D reconstruction and the limits. Because I'm saying from one single image you cannot get a 3D structure. You need many. How many are many? From the mathematical terms, it's very clear, an infinite number. How can I get an infinite number there? So if you are going to have a finite number, which errors are you going to have? This sort of thing like that, okay? So this is the basic of 3D reconstruction, and Carlos Oscar will be covering that tomorrow. Let me present you now perhaps a little bit more of the vision. Let me try to encourage you a little bit more. I mean, you are already very encouraged to come here all the way from this course, but let me try to push you a little bit more, just to tell you how exciting times we are in electron microscopy, how interesting it is to be in the field at this moment. And really, I say interesting times in many, many ways. I'm going to talk a little bit about image formation, image acquisition, algorithm, benchmarking, maps building and interpretation. What do I mean, image formation? I have told you about this projection and all that. Yes, of course. But what I'm now telling you is that really we were puzzled in electron microscopy for decades. If you put all the numbers, I will go into the slide. If you put all the numbers together, I mean, you have a wavelength of 0.02 angstrom, and the resolution was 20 angstrom, 1,000 times worse. How horribly am I doing every possible step in the way? Okay, the first step that we were doing very bad was how we were obtaining our images. We were having images that by the way they were acquired, the mechanism of acquisition was losing information. And it is only in the last 2 years that we have had the way to understand that by what we call direct detectors that actually have a very high efficiency counting electrons and are very fast. So we are able to record in 1 second 16, 20 images with much better signal to noise ratio than we had before. So far what I'm telling you, much better modulation transfer function than CCD, you know, this charge coupled devices for image acquisition. So I'm telling you, okay, we have a new generation of detectors that have much better efficiency than old generation. And you all expect this to happen. You are not surprised. And you are not understanding why I'm telling you that this has been a revolutionary change. The revolutionary change is because of the following. It was not so obvious at all. Is when you have your specimen, your biological specimen, in the preparation. Normally, I didn't talk about that, but in the electron microscope, and I suppose you know, the electrons have to go through vacuum. You have the source of electron, and you have the specimen, and you have to make the vacuum in between. So the specimen has to be protected with some stain. Some of you have made negative stains. Some of you have even gone to cryomicroscopy and has been able to make a solid thing, to put a solid specimen in the electron column. Okay? What we were not expecting so much was that as this block of solid ice or block of salt of uranium were irradiated, it was moving. It was moving. So it was moving in the order of a few Armstrong, a few degrees, enough to kill your resolution. So we were irradiating 2 seconds. During 2 seconds, a lot of movement happened in what you thought was a solid matrix. This was not moving. No, this was moving. Only that we had no technical capability to chop this 1 second into 20 slices and to see what was happening in 1/20th of a second. Now we have it. And now we see something that is called beam-induced movement. And this seems to be the reason why we were unable to achieve systematically atomic resolution in electron microscopy. Because here you see, look at that. This image from your place, probably you cannot say much. Maybe you are not so well trained, but anyway, this is a fantastic micrograph taken at a very good microscope in the world that happened every 100 times. So once every 100 times, in the best settings that you can imagine, you get one image like that. 99 times you get an image like that. Okay, with the technique that 99 times is making something bad, and 1 out of 100 times is making something good, you are not truly expecting to go to high throughput, okay? Because 99% of the time you are in problem. Which was the problem? Beam-induced movement. If you are now able to make many shots and correct the movement, you get almost 100% of the time the good images. So this is the revolution. So exciting times. You are at the very moment in which we know what has been hitting us with all this year and how to overcome it. Then,
sorry, this correction is a mathematical correction of the
it's a mathematical space or a real space. The first thing is that you are able to collect what now we call movies. So instead of getting one single image, we take 16 or 30. That depends on the device. And we call it movie. And then you take each of the frames of the movie and you try to put them in place. You try to correct the movement in a local or global basis. Okay? So this is the way to do it. There are still several approaches to that. We think we have one that is very good, but it's still work in the doing or in the making. Then you remember this limitation of optics. One infinitesimal point was not an infinitesimal point at the end of the optical system. It was a big point. Can I make it smaller? Okay, one of the ways to reduce aberrations. Come on, you have a wavelength of 200th of 1 Armstrong, and your resolution in material science is 1 Armstrong, and normally in our case several or 1 nanometer. So we were 1,000 times worse because of the aberration. Please try to reduce aberration. Fantastic. Now we are able to reduce one of the aberration, the CS, the spherical aberration. Finally, this is a work in the last 10 years, finally we know how to correct for the CS. And you may imagine, is by making the lens better. Okay? No. Is by making another lens that corrects for the bad things that were and are still being introduced by the magnetic lenses that we don't know how to do them better. But we know how to introduce an extra lens for the CS correction. We are able to play with the phases. I didn't go in, you don't have information with what I've said to go into this slide, okay? Because I tried to be very simple, and I leave that for Javi, that anyways is the next session. But this point spread function, in electron microscopy, we normally work in Fourier space, and we call it contrast transfer function. I'm not going to get into that. It's what is called zone plate, but it's actually something that is happening now, genomics, proteomics, things like that, as high throughput technologies. And how was this possible? First of all, because finally the microscopes are very stable. So now you can have microscopes that keep the vacuum, that can keep many things for hours and days. And because you have a microscope that is stable, now you can put software on top of that stable instrument to control it. Because it's going to be the same instrument for the next day. And with this combination, now you can really go into automated software for image acquisition. Software that will be checking if the grid is okay, where do I take the images in the grid, which images are good, I'm working overnight, I'm working over the weekend, I change the grid, and at the end of the day, I give you the best images. So this is a high throughput approach that really is paying a lot, and is going to be the basic of how we are going to work, how we are working already, and how we are going to work more in the future. Before, in the US especially, there were some infrastructural centers. Now in Europe, this is what we are going to have, 4 or 5 infrastructure centers in which the best microscopes are going to be there, and the access to those microscopes is going to be fully automated. And really, you are going to be running the whole thing for hours without touching anything, and with a lot of controls going on behind. And also automation also talk about processing, image processing, that is the topic of this version, in a very integrated manner. It's not only one operation, it's a complete series of operations in workflow. And you're going to see how everything we do here is in the range of workflows. Algorithms. We are in an extremely exciting time with the algorithm in 3D electron microscopy. And it's because of the following, and some of you are already coming from crystallography. In crystallography, you have a very well known and very well characterized sample that you know how it works and you like it, like a port 911. But you are starting to work with that sample, so you don't know really if that sample, when it is raining, it just changes. And there is something here that in a sunny day does not appear, but suddenly, when raining, appears. So there is a conformational change that happens in certain conditions that you yet do not know, so you yet do not control, that change the 3D structure of your specimen. Another challenge that we have is that cell biology is doing fantastically. It's a growing field, but I don't know how many of you have tried to work with cell biology at the structural level. Really, it's very complicated. It's very complicated because you can have a fantastic sample that is absolutely functional, because 10% of your specimens are like that and 90% are like that. And actually, it's very difficult to sort all these different conformations. How are we going to sort them? Well, finally, we have been able to. Well, and of course, the classification is intrinsic. Here I'm putting a number of examples that are about conformational changes, things like that, but movement conformational changes are the basic of function. So what you cannot expect is that a static structure is going to be telling you how function is happening. You must have a snapshot coming from whatever way you have. By that structure in conflict with X ligand, whatever condition, or by analyzing huge data set in electron microscopy. And actually, the situation in electron microscopy is that we finally have algorithms that can sort all this conformation and really give you the understanding of the dynamic of the system. We are not yet there for everything, and we have many problems, okay? But we have the automation. We have the capability to have images that systematically are good to the Armstrong. We systematically now have the capability to sort different conformations, giving you idea of the dynamic. And this is easy? No, this is complicated. And for that, somebody will be telling you about that. It will be Carlos Oscar, and it will be tomorrow at 10. Okay? And just trying to push you to say, listen, this is very interesting, and really, if you wanted to be able to study conformational changes, this technology is now able to provide with a lot of input in that direction. Of course, we have many algorithms, and we need to sort this algorithm, and we are doing what we call benchmarks. That is actually centralized ranking of how certain algorithms behave for certain data set and things like that. What I'm showing you is what we are at this moment. We have already finished in collaboration with Weiler, is the benchmark on point spread function estimation. But in electron microscopy, I was telling you, we talk more in the Fourier space, so it is contrast transfer function estimation. So this is from the technological point of view to tell you how good choice you have done coming here. But it's not only from the technological point of view, is that really electron microscopy is fantastic at this moment to be a hub of information. Information coming from many different sources. I was telling you, our dear colleagues of cellular biology, that have done so much with the confocal microscope, with the tagging of the molecule. So they have revolutionized our way to see the world. Okay, electron microscopy indeed is getting integrated into light microscopy. And in which way? For many things. Let present you a real flow of something we do with the, especially for the X-ray microscope in the microscope. You have a certain electron microscopy grid. For those of you used to electron microscopy, you will say, what a strange grid. Okay, is that these are just strange grids for other matters. But you see how the grid is at the optical microscope. Here you see how it is in the optical, but with fluorescent. So you see that we are interested in following a virus inside the cell. So you see, well, that I see membranes, I see green where the virus is. So I say, listen, I want to look by X-ray microscopy that specific part of the sample where I know that my virus is by fluorescent microscopy. Perfect. So this is a cell that has to be full of viruses, just by the fluorescence that I am measuring. No problem. I can go now to the electron microscope. I can go to the X-ray microscope of that very sample, of that very spot, and now analyze it at high resolution. Because here, you are limited by diffraction. Here, you are limited by diffraction, fine, but your wavelength is so small that you are not limited by diffraction. You are limited by anything else you can imagine, but not diffraction. So I am really able to follow things with the optical microscope, with fluorescence, I am taking profit of cellular biology development while I go into the high resolution structural biology part. How do I do it? Well, I suggest two approaches. The first one is the one we do, and is probably the easiest one. It's just a cryostate. That is some device where you put your grid, and where you put your grid here, and the liquid nitrogen and everything, and you see here with the microscope. Okay? So this is a cryo grid that is kept cryo, and you can look at the grid with the optical microscope. And later on, you take the grid here and you go to the electron microscope or to the X-ray microscope. Okay? So the same grid is being imaged under different technologies. Of course, you can imagine another way that is also being done, only that time will say if it is the most successful approach, is to take an electron microscope and to put by the side an optical microscope. And this is actually the design. You have here the objective lens of the optical microscope that is by the side of the electron microscope. So you have an optical microscope at the same column that the electron microscope. You need to design the whole thing, and this is, while this is costing a very few thousand euros, 2,000 or 3,000 euros. Here we are talking of a few 100,000. So, but things are different, and maybe you. But the key message is: do you like the cell biologist's work? Fantastic, because really you can now go with the same tools and take profit of everything they have developed to try to reach high resolution on the sample and on the spot, about the timing, about all that information. Now you can make the transfer very easily. Integrating with X-ray microscopy. This is actually the Spanish synchrotron ALBA. All these buildings try to be designed in a peculiar manner. So this is designed, supposed to remind you of a snail. The escargot, or well, to me it does. So here you know how this thing works. So you have the electron going around producing photons, and in different parts you have the end station, which one of them is the electron microscope, and this is really how it is an X-ray microscope. The fact, well, do you know how long is this? It's about 10 meters, okay? So it's a little bit bulkier than the electron microscope. There are only 3 in the world. And the amazing thing of the optic is that everything of the specimen, objective, everything is in 2 centimeters. Okay? So you have 10 meters, but everything happens in 2 centimeters. Is the optic. We cannot do anything about that. Okay, but this is fantastic because it allows us to look at whole cells. Whole cells. 10 microns thick cells. Okay, let's go to the other extreme, interaction. How are we going to incorporate information in electron microscopy? You are coming, some of you, from X-ray diffraction, fantastic. We may be looking at a larger complex by electron microscopy, and we can put into that complex X-ray diffraction information at atomic resolution of a piece, or NMR information of a piece at atomic resolution, and then this is the type of integration that you do. You have what we call the envelope, the 3D map, coming from 3D electron microscopy. You have pieces coming from technologies able to provide atomic resolution, typically NMR and X-ray diffraction, and your task is to put everything into here. Easy? Not at all. Not at all. And because of that, somebody else will go over that. Joan. Tomorrow, Joan will take you over fitting. We will probably also introduce you what we are doing in fitting. just as a way to show you where we are and where we are heading. But basically, the interaction with atomic information. But I'm pretty sure all of you at some moment you have gone to the NCBI, in Europe to the EBI, European Bioinformatics Institute, you have thought about PDB, Protein Database, you have seen any of the many databases that are around. And you may have imagined, wouldn't it be nice to have a 3D structure and at the same site to have all the annotations coming from bioinformatics databases? And this is exactly what we have done. So really, the integration is very good. You select either, well, you have here many annotations. You can make the question, what is happening here? That all these strange things at the annotation level happen. Where is that residue? And you see here. Or you ask, this strange residue, this strange look, which feature, what other information is known about that? And you can be here. Okay? So, and of course, this should have an impact in pharma. Should have an impact in pharma. The people of you coming from X-ray diffraction, you know that pharma is already there. In the case of electron microscopy, our soft, until now relatively limited resolution has made more complicated the interaction with pharma. But this is Novartis vaccines and diagnostics, so really the pharma is getting into that. And with the new direct detector devices, what I'm showing you is probably the first molecule solved by electron microscopy in December of a relevant at atomic resolution of a clinically relevant molecule without any prior information, just coming at atomic resolution from electron microscopy, not from 2D crystal or anything like that. And pharma means also money, okay? Means funding, means who you can approach, things like that. So exciting time. So very good choice of timing for coming here. It's winter, so it's a little bit cold for us. Not exactly now here in this room. And of course, we do not pretend that you leave this course just with theoretical understanding. So everything is going to be done in practical work, and the way to do things in practice is using some software. And you are going to use our homemade software that is called ISMIT 3.1 at this moment. And you will be exposed a little bit to something that we call a CPM. Well, what is ISMIT? ISMIT is the software that we have been doing during the year. The first release was 96, and at that time this was ISMIT. So it was a collection of tools. Tools to make a number of things, tools that really had a lot of expertise to make the tool and required a lot of expertise to use it. Well, then, of course, we put more tools. And so these tools now require even expertise to know which tool to use. So we thought, well, perhaps the average user, we are not making anything good. So we put a layer on top of it that said, can we guide the user with protocol? This was 2.4, and now 3.1, the global vision, as I say, is a graphical interface, project-oriented. You see the different steps of the process in a hierarchical manner. You can, from any point, you can branch in several directions, choosing different parameters, and check. And everything is logged, everything is reproducible. You will never need to think again what did you do. So, for some of you who are already in the field and know about the software for detecting conformational changes, this 3.1 also includes or integrates packages like Relion and things like that. Also, for those of you that, for many of you, you have worked with structures at some moment in your life. Chances are that you have used Chimera. Okay, so Chimera and XMIP, our software, they communicate in a, for you, transparent manner. So we call each other, and so you are seeing the 3D volume with Chimera, and I wonder, and how the 2D projection of this volume from this direction, we computed for you. So here it is the 2D projection computed with XMIP, while the 2D volume is being visualized with Chimera. Everything transparent. Because something very interesting is that the field of electron microscopy is now exploding into users that are not anymore willing to learn about the tools. They are willing and eager to know about the biological problem we want to solve, not about the tools. So really, it is our task to make it easier. This is the home page of the software. And then learning from Scipion, from XMIP, we are doing something else that you are going to be exposed in the last session. We call it the Scipion. Scipion is a very well-known Roman general that one of the Scipions had a very big victory, as you know. But Scipion is not another. We don't want to have another software package. It's just to make the life easy. It's an integration of packages. So it's an environment in which you can say, listen, it's fantastic what you are doing, but I really prefer that other method for no problem. Use that other method. And this will be another box, another step, done with another package that transparently we offer it to you. And you can link that other package, that step, to your previous, to your posterior. So what we are trying is really to simplify the view of different software packages in the field with a software integration. This is part of our duties in the Instruct project, in which we have to offer an infrastructure for European project, and the project do not need to know about different packages. They just want to have workflows with the best steps in each of them. You are going to see how a Scipion looks, which is very similar than XMIP. It's only that the steps can be from Spider, can be from email, can be from a number of different packages. And this will be presented by Jose Miguel. And this will be the last talk. And with that, I really finish. I finish again with the logo of Instruct, Integrating Biology, what we hope will be the future for the next 10 to 20 years of the way to offer infrastructure for structural biology in Europe.